depends on the quality chosen by the firm at period T, but it may depend also on what is the quality that the product has at the beginning of the period, okay? For instance, because they are convex cost of investment. That depends on the difference between A and K, okay? You can think that increasing the quality of the product, the cost of increasing the quality of the product increases more than proportionally between the difference between the quality, the new quality, and the old quality of the product. Okay? Then we have this investment cost, we have this variable profit, and the difference between the two give us the profit of the firm at period. And we can think that quality evolves according to some transition rule. The simplest transition rule will be this deterministic transition rule. Basically, in this case, A is an investment decision. A is the quality at the beginning of the period. A is the investment in additional quality that can be positive or negative. There may be downgrading the quality of your product. And this is the product quality for Nestle. Yeah? Okay, more generally, we can think that the exogenous state variables follow a Markov process, and we can think in more general versions for the evolution of the endogenous state variables. The simpler model, for instance, in a model of market entry, is that KIT is just the indicator, the dummy variable for whether the firm was active at previous period or not, because this is what determines if the firm will have to pay entry costs in order to be active in the market at period. But you can have other transition. This is the one that I have mentioned before, a deterministic transition, but with some depreciation rate, and also a stochastic transition where there is some stochastic depreciation rate. And you can think in different. I'm going to use Fx to represent in a compact form the transition probability of all the state variables, the endogenous and the exogenous state variables. Okay, Markov perfect equilibrium. Before I introduce the Markov perfect equilibrium, let me introduce a very general Nash equilibrium in this dynamic game. And then we will see that Markov perfect equilibrium is a particular case of this Nash equilibrium. Okay? Then suppose that we make the assumption or impose the restriction that when players make a decision rule, okay, or a strategy, okay, they consider strategies that depend on a particular vector of the history of the state variables that I call calligraphic T. Okay? And player J, and suppose that player I believes that all the other players, okay, they have also this type of strategy. Okay, they are going to behave according to some strategy functions that I represent as alpha J of this information at period T. Okay, for instance, to make it more concrete, this information at period T that affect the strategy function of a firm consists of the state variables that affect the profit at period T, but also state variables 1 period before, 2 period before, and so on, 3 period before, but also the actions of the players 1 period before, 2 period before, and so on, 3 period. In principle, we could consider, as long as you want, history of previous state variables and previous decisions. Say, suppose that players play strategies that condition on this information, okay? Then given this alpha function, these strategy functions, we can define this indirect profit function of a player I that now depends only on its own action, because basically it's taking into account that the rest, this is a typo, okay? This would be calligraphic IT, and here also calligraphic IT, okay? And we have this indirect profit function that depends on the action of the player, but also on this calligraphic IT, because we have condition, the player takes into account the other players will behave according to this strategy function. Similarly, we can define, basically, given that the other players behave according to this strategy function, we know what will be the transition probability of the state variable x at previous period, taking into account that today the other players will behave according to this strategy. And taking into account this strategy function and this definition of the information at period t, is straightforward to see that this implies a transition probability for this information at period t plus 1. Okay, then basically everything in the information at period t plus 1 that is not the action of the players at period t and this at period t is incorporated also in this information at period t. Then basically this transition probability here for x t plus 1 implies a transition probability for calligraphic I, okay? And we have a payoff function that depends only on the action of the player and calligraphic I, and a transition probability function that depends only on the action of the player and calligraphic I, okay? And basically taking into account these two objects, we can define a single agent dynamic programming problem, okay? And basically taking this payoff function and these transition probabilities of state variables, we can define this Bellman equation. The value of a firm or a player at period I, given this state, is the maximum over all the possible actions of this intertemporal utility. That depends on today's payoff. Again, there is a typo here. This would be calligraphic IT, and the continuation value, that is this term here, okay? And this is now taken as given the strategies of the other players. This is a single agent dynamic programming problem with a unique solution as any single agent dynamic programming problem with discount factor smaller than 1, okay? Then we can define the best response function of player I as the solution, the strategy function that solves this dynamic programming problem. And we can define it as the best response to the strategies of the other players. That is taken as given the strategies of the other players, the solution of this dynamic programming problem is the best response of player. Then given this, we can define simply an as equilibrium in this dynamic game as an n-tuple of strategy functions, okay, where everybody is best responding, taking as given the strategies of the other. And we have Nash equilibrium in a dynamic with an arbitrary choice for what the agents are conditioning to when they are constructing a strategy. Then you can consider any particular choice of calligraphic IT, and we will have a dynamic game with a particular type of Nash equilibrium conditional on this type of information. Okay? Then basically, all the results that I'm going to present here about estimation and solution of these models, they apply to this model. Of course, the computational cost will increase when we increase the dimension of this calligraphic I vector, okay? And that is one, not only, but one of the reasons why we are going to focus, or the literature has focused on Markov perfect equilibrium. What is Markov perfect equilibrium? Well, it's this Nash equilibrium concept when we restrict calligraphic IT to be XT. That is, players play strategies that depend only on state variables that are payoff relevant at period T, that affect the profit at period T. If they do not affect the profit at period T, they are not payoff relevant, okay? They do not have a direct effect on your profit. They will affect your profit only if the other believes that you are going to condition on this other variable. Okay? And okay, then that's the concept of Markov perfect equilibrium. And since the work of Maskin and Tirol in Econometric, and then in the context of I/O, the very influential paper by Erickson and Pickles, basically most of the literature on empirical dynamic games, dynamic discrete choice games in particular, they have followed this equilibrium concept. Okay? Two main arguments for this. First is the theoretical argument of rationality. That is the argument by Maskin and Tirol. And the idea is that if we think in a metagame that includes this game as a particular stage of this metagame, and the metagame includes basically the choice of information that agents can choose, basically the choice of calligraphic eye. How much information do I want to condition on in my choice of a strategy? Suppose that there was, before this dynamic game, there was also a choice of the calligraphic eye, okay? What Maskin and Tirol shows is that if the rest of the players are playing strategies that depend on payoff relevant variables, there is not any benefit for you to condition on information that is not payoff relevant, okay? And using payoff relevant state variables is a best response if the others are also using payoff relevant state. It is not the case if the other players are using less than the payoff relevant state variable, that is, if they are not conditioned on the whole vector X, there will be benefits for you of conditioning on more information than your opponents. But if your opponents have conditioned this strategy only on X and nothing else in the path, there are no benefits for you to condition on further information that is not. Okay? And this is this rational type of justification. Basically, you can think that Markov perfect equilibrium is an equilibrium within this game, this meta game that includes basically the choice of information, okay, that you want to use. Okay. The other, and perhaps very important, as I have mentioned today, it reduces substantially the dimension of the state space. Okay, it comes with a cost. Is that though Markov perfect equilibrium can generate equilibrium that can resemble type of coordination, okay, or if you want collusion in one cases, it's going to be easier to generate collusion in games where there is this type of non-payoff relevant state variables that you can condition on, okay? Then in some empirical application, it might make sense to say, okay, I'm going to go beyond Markov perfect equilibrium, and I'm going to assume that these guys condition not only on XT, but also on the previous state and the previous action, okay? Of course, now it will become more an empirical question or kind of arbitrary how much we condition on the past. Please?
So in this case, the choice of the specification of the state space is not arbitrary. It's the state space is fully defined by the profit function.
Exactly. In terms of the Markov perfect equilibrium, is not arbitrary.
So this
it comes from your specification of the profit function.
Yeah, but once the profit function is specified, the state space is specified. But then this means that, for example, in a prisoner's dilemma, right? Repeated prisoner's dilemma.
We will not have trigger strategy.
Exactly. It means that you do not have state, and therefore you cannot have. Okay.
Exactly.
So the idea is
now, notice that in prisoner's dilemma is not a dynamic game; it's a repeated game.
Yes.
Okay, there is no reason for that. Then, when we introduce dynamics, there may be strategies that can resemble type of punishment type that are Markov perfect equilibrium that can resemble type of trigger strategies in the prisoner dilemma type of thing.
But you need to have dependence.
Exactly. You not need to have true dynamics.
Yeah.
Exactly. Yeah. Great point. Yeah. Okay. Okay. Then let's go for the rest of this lecture. Let's go with Markov perfect equilibrium, but let's keep in mind that potential flexibility. Okay. Then basically, this is the same equations that I have written before. This is the Bellman equation. Taking as given the strategies of your opponent, you have this single agent dynamic programming problem. The solution of this Bellman equation for player I defines the best response strategy for this player, taking as given the strategy. And the strategies of their opponents basically determine this payoff function for you that depends on the strategies of the other, and this transition rule of the state variables that now take into account also the strategies of the others. Okay? But once we have solved these strategies of the competitors, in my payoff and in my transition probability, I have a single agent dynamic program. Okay? Okay? Now, so far, the games that I have described are games of complete information. At every period t, every player knows perfectly the state x. Okay, there is no private information at all. Okay? In a paper in Running 2010, Doroselsky and Satterwhite saw that, contrary to what Ericsson and Pekes claim in the RStat paper, there may not be equilibrium in this type of models with Ericsson and Pekes is complete information. Doroselsky and Satterwhite saw that with complete information, there are relatively simple examples and realistic examples where this model does not have, with discrete choices, does not have an equilibrium. Okay? Then, of course, we could guarantee an equilibrium if allowed for mixed strategies, but mixed strategies in dynamic models is tricky. Then instead of considering mixed strategies, they consider what other papers before Doroselsky and Satterwhite in the context of dynamic empirical games considered is incorporating private information. Okay? And we will see how we incorporate it. Okay? Then with private information state variable, with some state variables that are known only to player I but not to other players, equilibrium existence is guaranteed in this type. Then this is one of the reasons why the empirical literature on dynamic games have focused on dynamic games with incomplete information, with some private information state variable. The other reason that is at least as important as equilibrium existence, or even more important, is that this private information source will be a particular simple way to rationalize the behavior of the individual, basically to explain why two individuals or the same individual in two different periods of time with the same state, observable state for us as researcher, they have chosen different actions. Why? Because there is this private information shock that we do not observe as researcher and can explain. Okay? And this is the role of the epsilons in single agent dynamic model. The problem is that if we incorporate these epsilons in dynamic games and we consider that these epsilons are common knowledge, that type of game is much more complicated than that allowing that the epsilons are private information. Because now the epsilon of a player, okay, if this epsilon is common knowledge to the player, is not going to affect only his own action, but also the action of the other player. Okay? And that can make the analysis much more complicated. Then incorporating private information shocks that are unobservable to the researcher is a very simple and convenient way of basically rationalizing the heterogeneity in consumer behavior across individuals and over time. Okay? Of course, it eventually is going to be an unobservable. It's going to be very restrictive to assume that that is the only unobservable. Okay? Because it assumes conditional independence of the action of the players and conditional independence over time. And we know that typically data sets are going to reject that independence. But that's a different issue that I'm not going to to consider in this lecture. Okay. Then dynamic games with incomplete information. Basically, we are going to assume that there are these additive epsilons in the payoff function that I'm going to denote as epsilon, that is private information of the firm, and they are IID over time and across players. Okay. Then the strategy function of a player is going to depend not only on the common knowledge variable X, but also on the private information X. Okay. It's convenient to define, given the strategy of a player, it's convenient to define the strategy in a probabilistic way, basically conditional on the common knowledge information for all the players, that is also the observables from the point of view of the researcher. What is the probability that a player chooses a particular action? Okay, this probability. Okay, then basically it's the strategy function integrated over the epsilon. Okay? Given Hodge-Miller invertibility property, it's possible to show that there is a one-to-one relationship between these alphas and these choice probabilities. Given strategy function alpha, we have a unique CCP function, of course, but also given a CCP function, it's possible to show that there is a unique strategy function, because we know that the conditional independence implies that the epsilon will enter additively in this strategy function. And basically that is going to uniquely identify this strategy function. Okay? Taking into account that there is a one-to-one relationship between strategy functions and CCPs, then what I have described before as the pi alpha and the F alpha, that is the payoff function of a player taken as given the strategy of the other players, we can describe it using the choice probabilities of the other player. And taking into account the choice probabilities of the other players, what is the expected profit of player I if he chooses alternative? And this is just the result of integrating over the actions of the other players using the choice probabilities of the other. And similarly, taking as given the choice probabilities of the other players, I can construct this transition probability for player I, for the state variable, from the point of view of player I. Okay? And what is the transition probability of X, taking into account that the other players will behave according to these CCPs at period. Okay? And taking this expected profit and this expected transition probability, I can construct this conditional choice value function, okay? And I can define also this integrated value function, okay? In this context, a Markov perfect equilibrium can be described not only in terms of the strategies alpha, but we can define a Markov perfect equilibrium in terms of vector of choice probability. Then, given this conditional choice value function, what is my expected profit today and in the future if I choose this action today, taking as given the choice probabilities of my opponents, okay? Basically, I take in this conditional choice value function, and my choice probability today should be the result of integrating my best response function today, integrating over the distribution of epsilons. Okay? And basically, these mappings describes the choice probabilities of player I as a best response to the choice probabilities of the other players that we have used to construct this expected profit, expected transition, and then expected conditional choice value function. Okay? Then the model can be described as a fixed point mapping in terms of the CCPs of all the players over all the actions and over all the states X. That's what this compact fixed point mapping represents. Okay? Basically, this mapping for every player I, every action A, at every state X. Okay? This best response mapping psi that I'm using here is a continuous function. P belongs to the simplex, that is a compact space. Then by Brouwer's theorem, it's clear that an equilibrium exists in this game with private information. Okay. In general, models, dynamic games can have many, and that is going to be an issue in potential issue in estimation, and especially in counterfactual expression. Okay. But we have that with incomplete information, we have an equilibrium model. And in principle, conceptually, it's very easy to calculate an equilibrium in this model, for instance, using best response fixed point iterations in this model, if there is comparison. Okay. A particular example, suppose that these epsilons, private information epsilons, are a string value type 1 distributed, then the best response function of a player is this logic probabilities. This is the conditional choice value function, and the value function here of a player is just has this McFadden social surplus expression that is the log of the sum of the exponential of this conditional choice value function over all the possible choices. Okay. Then we can think in relatively simple algorithm to calculate an equilibrium. Of course, there is a course of dimensionality as usual in the computation. Okay. Okay, let's talk about estimation of this model. Suppose that we have panel data for A and X. Basically, we observe these firms playing this game over capital T periods of time, and we observe them in different geographic markets. Okay. Our goal is to estimate the parameters of the model. In principle, the parameters of the model include the parameters in the payoff function, the discount factor, the transition probabilities of the state variables, and the distribution of it. Let me use theta to denote all the structural parameters that we could basically distinguish different components, the structural parameters in the payoff function, in the transition probability of the state variables, and in the distribution of it. Okay? Please.
Yes, so sorry, it's actually on the previous slide, but when you said yes, so is this a consequence of IIA, or is it just an example and it works with a nested logic or a probit as well? Like if the epsilons are normal, for example, then they'll hold just with the
you mean the equilibrium resistance?
No, your example there. Yeah, exactly.
Equilibrium resistance will be the case for any distribution epsilon that has continuous support over the whole Euclidean space. Okay.
So you just made an example with the, and then, for example, if it were normal, then that would be the.
Exactly. We will have, if we have a binary choice model, then we will have here basically the CDF of the standard normal.
Yeah, exactly.
With multinomial normal, of course, we don't have a closed form expression for this.
Normal would be yes, but I'm thinking of the
But with the nested logic, we will have also closed form expression for this problem.
Okay.
And we will have also closed form expression for the McFadden social. Okay, the parameters in the transition probabilities of the state variables in this model can be estimated outside of the dynamic model just by looking at the transition data of X, and that's easy. Most of the papers assume that the distribution of epsilon is known, okay, or is known up to, for instance, in a nested logic as up to 1 parameter or so. And most of the papers assume that beta are also known, but we can revisit that later. Okay. Then I'm going to focus here on the estimation of the parameters in the payoff function of the okay. Then to understand the value of the sequential CCP estimation, I think that is worthwhile to see the difficulties associated with the full solution method, with methods that basically use maximum likelihood estimation and some kind of repeated solution type of algorithm. Okay. Then let me distinguish two different problems. The problem of multiplicity of equilibria, and even if we have single equilibrium, the problem of having to repeatedly compute an equilibrium of this. And to distinguish this between these two different computational challenge, let me start with models, dynamic games, that for every value of the structural parameter theta, we have equilibrium. Okay? Then the first question is, well, do we have that type of dynamic gains within this class? Can we guarantee, can we impose some restrictions such that we have equilibrium uniqueness? Well, there are some papers. I think that my colleague Michi Igami has been the main advocate of that approach. There's empirical applications of dynamic gains where they impose restrictions that they guarantee that for every value of the structural parameters, we have a unique Markov perfect equilibrium. Okay, which are these restrictions? Okay, these are not necessary, but they are sufficient restrictions. Okay, I think that they are close to the necessary, but anyways, okay. The first restriction is that we have finite horizon. Okay, there is a finite number of periods, and everybody knows that we will be playing this game for 100 periods. Okay, and the second assumption is that at every period t, players play sequential. Okay, and first player one moves first, then player two, and so on. Okay, of course, who plays first matters. Okay, and then there should be some justification for this assumption. Okay, it's quite straightforward to show that if we have a finite horizon, if we are at last period at capital T and players move sequentially, we will have a unique. Okay, we can argue, use backward induction to show that there will be a unique equilibrium, unique optimal strategies at the last period. But then we can use again backward induction and go to period capital T minus 1, and the same applies. Okay, then we have a unique Markov perfect equilibrium for this type of game if we assume this finite horizon and sequential move within each play. Not going to try to argue that this is a reasonable assumption or not, because I'm not a big fan of that approach. Okay, but okay, let's suppose that we have a model where we are willing to make that assumption and we have equilibrium uniqueness. Okay, then that means that for every value of the vector of the structural parameter theta, we have our model predict a unique vector of choice probabilities for each player that are the choice probabilities under Markov perfect equilibrium. That means that we have a well-defined likelihood function. For every value of theta, we have a function, a unique vector of choice probabilities, a unique function that includes the choice part of the data and also, in principle, the transition of the state value. As I mentioned before, I'm going to ignore this part of the likelihood function, and I will focus on this part. Huh? Then, in this context, we can use a standard nested fixed point algorithm, and that's what these applications are using these assumptions they have used. Okay, we use a nested fixed point algorithm where at every outer iteration we make a BHHH step to maximize the likelihood function. These are the scores of the likelihood that I have presented before. And at each inner iteration, for the candidate theta hat value at that iteration for the vector of the structural parameters, we solve for the unique Markov perfect equilibrium that give us the vector of choice probabilities and the corresponding scores. Okay? Then we iterate in this procedure until convergence, as in single agent dynamic decision. Okay, the only difference is that now we need to compute at each inner iteration at a Markov perfect equilibrium, which involves solving many times dynamic programming problems. Because as you can imagine, for the solution of for the typical approach to obtain a Markov perfect equilibrium is basically a fixed point iteration approach, is that you start with strategies of the opponents, given the strategies, the choice probabilities of the opponents, you solve for the dynamic programming problem of a player, you do that for all the players, that give you new choice probabilities of all the players after solving all these dynamic programming problems, but then you should go back because the best response of player one does not correspond to the belief that the other players had at the previous iteration about the choice probabilities of player one. Okay, then you need to iterate here until convergence, and there may not be convergence. In contrast to the contraction property of the single agent dynamic programming problem, each single agent dynamic programming problem is a contraction, but this mapping in terms of their responses, okay, this mapping is not a contraction. And that's why we can have multiple equilibria. And it's not only that we can have multiple equilibria, it's that a fixed point iteration in this mapping is not guaranteed to converge. Okay? And there are issues in the computation of this of a dynamic, not to mention the course of dimensionality. The course of dimensionality in dynamic games is typically more severe than in single agents, because if for each agent we have 10 possible states or 100 possible states, for the whole state vector, we will have 100 to the power n, where n is the number of players. Then very easy, even if the state of each player is very small, we can end up with 5, 6, 10 players, we can end up with a dimension that is larger than the number of atoms in the universe. Okay, then the course of dimensionality in dynamic games can be very severe. Okay. Okay, then this is typical computational cause of course of dimensionality in dynamic decision models, but at a different level because the state space typically is larger in dynamic games. Okay? Let's incorporate now the additional difficulty that is the fact that for at least for some values of theta, we have multiple equilibria in this model, unless we impose the strong restrictions that I have mentioned. Yeah? Then Doraszewski and Satterwhite in a paper in theoretical economics in 2011, they saw that this class of models, they generically have, for every value of theta, they have a finite number of Markov perfect equilibria. Okay, and we can count, and this is finite, the number of equilibria that they can have. Okay, then let me use calligraphic P to represent for a given value of theta all the different Markov perfect equilibria, the vector of CCPs that are Markov perfect equilibria for this particular value of theta. Okay? And what I'm trying to argue here is, despite we have multiplicity of equilibria, the maximum likelihood estimator is well defined. In principle, we have a likelihood correspondence, but it's possible to define at the end a maximum likelihood estimator, despite we have a likelihood correspondence, because at the end we can condition on the type of equilibrium to have a likelihood function. Okay? But the problem is not that conceptually the maximum likelihood estimator is not well defined or does not have the very good properties of maximum likelihood estimation in general. The problem is, again, computational cost on the implementation of this. Okay? Then let me define this maximum likelihood estimate. Okay? Then suppose that for every value of theta, we have an algorithm, okay, that for every trial value in our search for estimating theta, for every trial value of theta, we can calculate all the Markov perfect equilibria of them. Okay? we can calculate P1, P2, and so on, P large. Okay? For instance, using the very nice recursive lexicographic search algorithm in the paper by Fedor, Bertelan, and John. Okay?
All study on Sunday.
Sorry?
We will all study on Sunday.
Excellent. Then the maximum likelihood estimator is, then we can define a likelihood function here that condition not only in theta, but also on tau, okay? And we can define a maximum likelihood estimator that maximizes not only with respect to theta, but with respect to tau, okay? Thanks.
How do you do counterfactuals after you estimate the parameters?
Excellent question, okay? Excellent question. That's a very good, that's a very important challenge, okay? There are ways of doing it, okay? This is a very serious challenge, but there are algorithms that use homotopy methods, and I have a paper with, I have used an homotopy method for it. Let me represent this homotopy method in a very stylized frame. Suppose that we have one single value of theta, and P is also one dimension, okay? Then suppose that this is the equilibrium manifold of the model, okay? Basically, what this tells us is that for a given value of theta, suppose that this is theta in the data, okay? In the DGP, okay? And for this particular value of theta, the model has equilibrium A, equilibrium B, equilibrium C, equilibrium D, and equilibrium G, okay? We have these 5 different equilibrium, okay? And now we consider, and suppose that we have estimated our model, and suppose that there is only one equilibrium in the data, okay? Suppose that that is the case. And this is equilibrium C, okay? Okay, this is the one in the data. This is our P0 in the data. Okay, then we have estimated theta 0, and this is P0 in the data. Okay, in principle, the model can have, and we didn't know, that's why in the maximum likelihood estimation, we need to try the different possible equilibria. But after estimating the model, we know that this is the true vector of structural parameters, and this is the choice probabilities in the data. Okay. Then suppose that now we want to make a counterfactual experiment. Okay. What will be, okay, the choice probabilities if we change theta from theta 0, from the one in the data, to theta star, okay? And now we have been able to identify in the data that we are here. But of course, now our model tells us, the recursive lexicographic search algorithm of Bertel and Fedor and John will tell us, well, in principle, we could move here, or here, or here, or here, or here. You can see in this example that the sign of the effects are even completely different, okay? Then what the homotopy method does? What the homotopy method is based on the assumption that these different equilibria can be classified in different types. What is a type of equilibrium? Is basically all the different equilibria that we can basically, okay, all these belong to, let me say, type A, okay? All these other guys over here, up to this singularity point, they are type, this is type A, this is type B, okay? All these guys between here and here are type C, and so on, okay? And there is a formal mathematical way of defining unambiguously equilibrium types, okay? Then what the homotopy method says is that we are going to do counterfactual or comparative statics under the assumption that this counterfactual experiment does not change the equilibrium time. We are going to maintain the equilibrium time. Okay? And then what the homotopy method will do is to move along this equilibrium manifold, okay, until we get to this point, okay? And that will be the counterfactual. And there is a single, okay, counterfactual associated with theta star that belongs to the same equilibrium type. Then once we condition on equilibrium type, there is equilibrium uniqueness. The idea is that we are doing counterfactual experiments and they're assuming that this counterfactual is not going to change beliefs in a very weird way, such that we are going to jump across equilibriums, which might be a reasonable way of doing counterfactual. Perhaps not realistic, but at least we know what we are doing in that counterfactual. The problem is that if this counterfactual is very counterfactual, okay, then we could end up here, okay, for instance, or worse, okay, we could end up in suppose that well, there is other one up there, and then basically we know that we can end up in a situation where the type of equilibrium that associated with our data no longer exists, and then we are back in the wilderness, okay? We don't know of this other equilibrium which one will be selected, okay?
Just a quick follow-up, is there a continuity assumption that you need for the
Of course, the homotopy method is based on a continuity function, but that continuity function is implied by the model, okay? By our assumption, basically by the continuity of the best response mapping phi of C, okay? That's implied. Okay? But this is an open question in the literature, and important. At the end, you need to make some assumptions about the equilibrium selection in the context of your counterfactual. Okay, then in this case, the nested fixed point algorithm or a particular implementation where you will learn much sophisticated methods with Bertel and Fedor about this. But let me suggest here a version of the nested fixed point algorithm with multiple equilibria. Basically, it's the standard version of the nested fixed point algorithm, but now at each inner iteration, we need to do two things. First, we need to solve for all the equilibria in the game, okay? For this trial value of the vector of the structural parameter theta. But then now we need to select which of these different equilibria has higher likelihood, okay? Then we can use the vector of structural parameter theta at the previous iteration, calculate all the equilibria that this model has for this theta, and using these choice probabilities, choose the one, the tau, that give us the highest likelihood, okay? And we say, okay, that is the equilibrium type, okay? And then given that equilibrium type, basically we have now fixed tau in a particular value. Now we maximize, we make a BHH iteration with respect to, we make a BHH iteration with respect to this theta star, okay? That is the one that we have selected, okay? Then conceptually, very straightforward way of doing nested fixed point algorithm. Of course, in terms of computational cost, now it has the additional computational cost of having to solve for all the equilibrium in the model, okay? Which can be quite computational, okay? Alternatively, we could use other method that is the MPEG method with multiple equilibria. Here, instead of considering the likelihood function for every possible equilibrium, what we do is to define a likelihood function that is not using equilibrium probabilities, but is using instead best response probability, okay? That is, suppose that we treat these choice probabilities as the beliefs that players have about the behavior of the other player, okay? then if I fix the beliefs that player I has about the behavior of other players, now, given fix my beliefs, I have single agent dynamic programming problems. This is like the best response functions, probabilities, from a single agent dynamic program. Okay? Then let's consider likelihood function that treat the choice probabilities or the beliefs of the players, okay, as parameters, okay, similarly as the parameters theta, okay? Then now, because these are not equilibrium probabilities, these are best response probabilities, this model has unique predictions about the best response probabilities of a player. The best response of a player is the solution of a single agent dynamic programming problem. This has always a unique solution. These are functions once we fix P, okay? Then let's consider that the estimation problem is one of estimating structural parameters and beliefs. Let's put it that way, okay? The beliefs that players have about the behavior of others, okay? And let's define a maximum likelihood estimator, okay, as a vector of structural parameters theta and a vector of beliefs P that maximize this likelihood function, okay? But now, importantly, we cannot estimate if we do not impose restrictions, we cannot estimate beliefs and structural parameters unrestrictedly, okay? But we take into account that our model imposes the restrictions that beliefs should be self-fulfilling in equilibrium, okay? That the beliefs that a player has about the choice probabilities of other players corresponds to the best responses, choice probabilities of other players. In other words, that these beliefs are an equilibrium of the model, okay? And we maximize this likelihood function subject to this constraint, which is equivalent, this is a Lagrangian problem, is equivalent to maximize, obtain the value of theta, P, and lambda that maximize this Lagrange problem, okay? The first order conditions of optimality of this Lagrange problem are these choice probabilities and structural parameters should satisfy the equilibrium condition, and then they should be, this Lagrange should be optimized with respect to theta, and importantly, this Lagrange should be optimized with respect to P, okay? Then what the MPEG does is an algorithm basically to obtain a root, okay, to obtain the value of theta, P, and lambda that solves this Lagrange condition, okay? As you can see now, the dimension of the problem is huge, okay? We have transformed a problem of optimizing with respect to a few structural parameters to optimizing with respect to theta, and this huge vector of parameters that can contain millions of choice probabilities, and the lambdas that has the same dimension as the P. There is a Lagrange multiplier for every possible value of the choice probabilities, okay? And this is a huge dimensional problem. The best way of solving the huge dimension problem is this Jacobian matrix, the Jacobian matrix of the best response probabilities. In general, these models do not have a sparsity with respect to this Jacobian matrix. The change of the choice probability of a player in a particular state and action affect the best response choice probability of every other player in any other state and any other action, okay? And computing these Jacobian matrices can be computationally very demanding, okay? And this is the main computational cost of the MPEG. And in my view, the main reason why this algorithm has not been in a serious empirical application for dynamics. Yes, in Mickey Mouse type of versions and Monte Carlo studies, okay? The dimension, high dimensionality and the cost of computing this. And we do not have numerical expression, of course, for this Jacobian. Okay?
Can I add one thing?
Sure.
Another thing about MPEG is it just finds one solution. So it says multiplicity of equilibria. You don't know.
Exactly.
Yeah. So
Exactly. Yeah. Exactly. I think that's a clear disadvantage with respect to this one. Definitely. Yeah. Okay, then let's consider other methods within the class of the so-called CCP or sequential method that can reduce the computational cost of estimating this model. Okay, let me focus in the case where, because this is where we get the main computational advantages of CCP method. Let's consider the case where the payoff function of the players are multiplicative in the structural parameter. Then we can write the payoff function of a player as a function of known, as a vector of known functions of the actions of the players and the state, multiplying a structural parameter. Okay? And these theta pi I are the structural parameters of. Okay? Then remember that this is the conditional choice value function, given that the other terms behave according to the choice probabilities in P. This is the expected value of the stream of future payoffs, okay? Discounted and taking into account that the evolution of this action will follow the choice probabilities of the players. And these actions, and therefore the selection of this epsilon, will be associated also to the optimal choices based on the choice probabilities. Okay? Then it's possible to solve their analytical expression using matrix algebra for this object. But to make it very simple, suppose that we use forward-looking simulation. Using the choice probabilities of the player, we use forward-looking simulation to generate actions of the future actions of the players in a recursive way. And then we can represent, in this model, we can represent the conditional choice value function basically as a linear index of the structural parameters and objects that can be estimated from the data. Okay? What is this H tilde? This H tilde is just basically this part here, the expected value of future vector H, taking into account that the evolution, that we are in a state X at period T, and we have chosen this action, and then the future values of the actions and the state variables will follow the transition probabilities of the state variables X and the choice probabilities in the CCPs of the players. Okay? And we have, this is a known object. Using choice probabilities and transition probabilities, we have an expression for this H tilde. This is data, if you want, okay? Once we have the choice probabilities and the transition probabilities, we can obtain this as a vector of explanatory value. And the same thing for this object, that is assuming that the epsilons have an extreme value distribution. That's why we have the Euler's constant minus the logarithm of the choice. Yeah. Again, this is data. This is an scalar that we can obtain for every action A and every state X. We can obtain it. Yeah. Then, using this representation, we have transformed our dynamic programming problem in a single agent dynamic programming problem, where basically the choice probabilities have this very simple expression. Okay? This is data. This is data. We can estimate theta just by using a standard multinomial choice model. Okay? And we don't need to repeatedly, we don't need even to solve once for the equilibrium of the model. Okay? We just have taken choice probabilities and we have used it to calculate these expected values. Okay? And these expected values. Okay? Let me say that if you use matrix algebra, basically the computation of this object, H tilde, it will involve inverting a matrix for player I, inverting a matrix of this nature, okay? Inverting this type of matrix, where this is the transition probability of the state variables for all the players, okay? Implied by the choice probabilities. This is the discount factor, and this is the identity matrix. Then basically, the dimension of this matrix is the dimension of x, okay, times x, okay, the dimension of the vector of state variable. And this is the main computational cause in solving for these guys. Basically, inverting this valuation matrix, okay? Alternatively, you can use forward Monte Carlo simulation, but that is going to be an approximation. This will give you exactly the values of these guys, okay? And of course, there is a course of dimensionality in the computation of this matrix, okay? But this is basically solving once for the best response of a player involves inverting this matrix multiple times, okay? If you use a Newton-Kantorovich iteration, okay? Then this is computationally even cheaper than solving once for the best response function of a player. In the nested fixed point algorithm, you have to solve multiple times for the equilibrium of the model, okay? Okay? And there are very substantial computational savings in using this approach instead of nested fixed point. Okay? Then how does the method works? Basically, we have this likelihood, this pseudo likelihood function, if you prefer, that I have described before, okay? Where we have these best response functions, these beliefs. We are going to estimate choice probabilities here, okay? Then this will give us estimated P. We have these values here, okay? That we have, that will become data, okay? And then we have a logit, multinomial logit model, a standard multinomial logit model to estimate theta, okay? And that's what this two-stage estimation of theta means, okay? This is what this expression means, okay? Estimation of non-parametric estimation of the choice probabilities, use these choice probabilities to compute present values, plug these present values here, and then a standard, this static kind of estimation, okay? What is an important limitation of this approach? An important limitation of this approach is basically finite sample properties of the map. We are estimating in many applications millions of choice probabilities, okay? Basically, what is the choice probability that a player chooses to be in the market, for instance, given that the vector of state variables of all the players takes one particular value? Typically, we have one observation in the data for each value of x, and only for a few thousands of the states. For all the other states, we do not have any observation, okay? And basically, of the millions of possible states that the dynamic game has, we observe only a few thousand. For each of these few thousand, we observe each state only once. And we want to estimate non-parametrically the choice probability, the probabilities of entry of the firm for every possible state. It's obvious that we are going to get very imprecise non-parametric estimate of the choice. And the reason why we want to be non-parametric here is not that because our model is non-parametric in any way. We are making parametric assumptions everywhere. The reason why we go non-parametric is because this is a reduced form of our structural model. Without solving the model, we don't have idea about how the choice probability depends on the state value. And that's why we need to be non-parametric, or at least flexible in the specification, okay? Then the question is whether we can apply this idea of the CCP estimation in a way that does not rely on this very imprecise initial estimate of the choice probability. Let me say that the problem is that garbage in, garbage out. If you start with very imprecise estimates of the choice probabilities P, your estimate theta hat will be consistent and asymptotically normal, but in a given sample will be super noisy and will have very high, large finite sample value. Okay, and value. Okay, and that's the problem. Then can we use this idea of the CCP estimation in a way that can give us estimates that do not rely on the initial non-parametric estimate? Hopefully that they do not depend at all on these estimates, okay? But they still imply substantial computational savings relative to the nested fixed point algorithm or MPEG method. Let's say the full repeated solution. Okay? Okay, and that's the idea that we exploit or we suggest, we propose in the paper with Pedro Mira in our paper in 2000. Okay, we call it the nested fixed point algorithm. Okay, or the nested pseudo likelihood estimate. Okay, the idea is the following. Okay, let's suppose that we define an MPL estimator as a pair of structural parameters and choice probabilities that satisfies two conditions. Okay, the first condition is that given P, okay, theta maximizes this pseudo likelihood function. Okay, then given P, we construct these present values here, and the theta that is our estimator maximizes this likelihood function of a static logit model. Okay, that's the first condition. Okay, then the two-stage estimator satisfies that condition. Okay, because we have vector of choice probabilities, and given that vector P, we have a theta that maximizes this likelihood. Okay, the second condition is that these choice probabilities should be in equilibrium. Of course, the choice probabilities that we are going to input as non-parametric estimates in the two-stage estimator will be very different to the predicted choice probabilities. That is, let me say that once we have estimated our model, once we know theta, and given the non-parametric piece, now our model, okay, let's think in this hat, and hat. Now our model has a prediction about what is the choice probabilities of player I of taking this action in this state. That will be the prediction of our model about the choice probability, which in general will be different to the non-parametric choice probabilities that we have input to construct these present values. Okay? Then what we are saying is that the predictions of the model should be the same as the choice probabilities that we have input. Okay, the belief should be self-fulfilling in the equilibrium. Okay, and of course the two-stage estimator does not satisfy this condition. The non-parametric estimate generally is going to be very different to the prediction of the model once we have estimated theta. Okay, then notice that these are kind of related to the conditions of MPEG, but we are avoiding the key restriction that is generating problems. Okay, and basically these are the restrictions, the first order conditions for MPEG. We are not saying anything about maximizing with respect to P, then we are not including these conditions at all. Okay, that notice that involve this large Jacobian matrix, and in this condition we are not including this term here. We are saying, okay, given P, we maximize with respect to theta. Then basically the two conditions of the MPL estimator is this and only this, without this, equals to 0. Okay? Okay, and then the question is, how do we implement this MPL estimate, and why it's going to be computationally cheaper than nested fixed point? Okay, one very simple way of implementing this estimator is basically applying recursively the two-stage estimate. As I mentioned before, once we have estimated theta, okay, now given our initial P, our estimate of theta, we have now this new vector of prediction of choice probabilities that, of course, they are much more informative than the initial choice probability, because they are using a lot of the structure of the. Okay, they are not imposing equilibrium restrictions, but they are imposing best response restrictions and a lot of parametric assumptions in our model. Then these new estimates, they should be much more precise than our initial non-parametric estimate. To start with, this model provides non-zero prediction for choice probabilities in a state that are not observed in the data. Okay, we can apply this formula for every value of x in the data or not in the data. Okay? Then why not using these choice probabilities to do again this two-stage procedure again? Now let's take these choice probabilities, let's construct new present values here, okay? Using these new choice probabilities, let's plug them here, and let's obtain new estimates of choice of the vector of parameters theta, okay? And let's do this up to convergence, okay? Until theta doesn't change. If we have convergence in theta, we have convergence in P, which means that we will have, at the end of this iterative procedure, we will have that the equilibrium conditions hold, that the new vector of choice probabilities are the same to the beliefs that we have used to construct this vector of choice probability. Okay? And that's basically, this is a particular, and this is the algorithm that we proposed in the 2007 paper. Okay? The definition of the MPL estimator is this. This is a particular algorithm to obtain this MPL estimate. That is basically iterating, given P, obtain theta, and given theta, apply this valuation to obtain new vector of choice probabilities. And do this until we get convergence. Okay? Notice that we are not solving for any solution of the dynamic programming problem, not to mention for any Markov perfect equilibrium at any of these states. Okay?
So unlike the two-step estimators, you don't need to start with a consistent.
Exactly. Exactly.
So why?
Of course, it doesn't damage it doesn't have harm to start with some non-parametric estimate, but we could start with any. And that is going to be important when we introduce an observatory N80. Because with an observatory N80, we have different types of individuals according to time invariant and observatory N80. We cannot estimate consistently the choice probabilities conditional on the observatory N80. Then for that is particularly important, because we can start with arbitrary vector of choice probabilities in principle, and upon convergence, you have a consistency. How much time do I have? Okay, several papers has challenged this recursive method. Basically, several papers, including our later papers, they have shown that this algorithm may not converge. Okay, which is of course a very important issue. Okay, then let me describe briefly different algorithms to compute this nested pseudo-likelihood estimate. And the MPL is defined in this way. Okay, it's a pair of theta p that satisfy these two conditions. Okay, this is a particular way of computing this, but as I'm going to explain, it has some computational problems because the possibility of not convergence. Then let me consider several. First, the MPL estimator, so is defined of both theta and p. We can characterize basically in terms of iteration of the choice probability. Then we can define the NPL estimator as a value of P that solves a particular fixed point problem. That is basically the fixed point problem that is defined by this mapping, where this mapping is, this is the best response mapping, okay, of theta, C of P theta is the best response mapping, and this theta hat is basically the pseudo maximum likelihood estimator, this very simple maximizer of Q of theta given P, okay? That is like a static model, like a standard multinomial choice model, okay? Then this comes from given P, let's solve for the maximal, pseudo maximal likelihood estimator given P, let's plug that theta here and let's obtain the best response, okay? The nested pseudo likelihood estimator should be a fixed point in terms of choice probabilities of this mapping, okay? And then basically that tells us that obtaining the NPL estimator is equivalent to finding a fixed point of that mapping that is not, because we have this theta hat here, is not just, it's not simply an equilibrium of the model, okay, involves estimation, but it's also equivalent to solving for a zero in a system of nonlinear equations, okay? Then that is what is going to motivate different approaches to obtain the NPL estimate, okay? Then let me discuss it here, okay, in this slide. Then the first approach, that is the one that we proposed and applied in our 2007 Econometric paper, is simply using fixed point iterations in this mapping phi, okay? Given theta, obtain theta hat P, then plug it in here and obtain a new P, and so on, iterate until converge. What is the problem? Is that phi is not a contraction mapping. And because it's not a contraction mapping, we may not get convergence, okay? That's the problem that several papers in some applications, they have some, okay? Then let's go to a representation of the NPL estimator as the solution of this system of nonlinear equations. If we are concerned about convergence, the best algorithm ever to guarantee convergence, quadratic convergence in some cases, but very fast convergence in very general cases, is Newton method, okay? Then if we want to guarantee convergence, let's apply Newton methods to this to solve this system of equations. And we are going to get the NPL estimator for sure with convergence. What is the problem of using Newton methods? That we need to use the Jacobian of this matrix phi. And this Jacobian is exactly what we wanted to avoid, okay? That's what MPEG needs and we don't need, okay? The Newton guarantees convergence, but at a very high computational. Then instead of that, in a paper with Matthew Marco in Quantitative Economics in 2021, we consider an alternative method that is the so-called spectral residual method. That are very general method to calculate system of nonlinear equations that do not have contraction properties. And they are methods that try to replicate the speed and robust convergence properties of the Newton method. But instead of using a whole matrix, by basically using a single scalar that is updated, okay? And let me, basically this will be, if we have our system of equations represented as Fp is equals to 0, this would be Newton's method. We need to calculate this Jacobian and invert this Jacobian, okay? Convergence is guaranteed, but at high computational cost, okay? Then this is the very simple idea of the spectral methods, okay? Where we use a single scalar alpha, okay? Then basically at every iteration, all what we need to calculate is exactly the same as we need to calculate for fixed point iteration, the function f, or the mapping phi of p, okay? And then at each iteration, we update these scalar alphas in a way that tries to, that under some condition is guaranteed that these alphas will converge to what is called the spectral radius of the matrix of the inverse Jacobian matrix, okay? The inverse of the spectral radius, that is the maximum eigenvalue of this matrix, okay? Then because, or if the conditions are satisfied for these alphas to converge to the spectral radius of this matrix, then the convergence properties of Newton iteration will be mimicked by this spectral radius, and convergence then will be guaranteed, okay? It's difficult to establish whether these conditions hold or not in the model, but in different Monte Carlo experiments and empirical applications, we have tried with success these spectral methods to obtain convergence. To obtain convergence where the fixed point iterations, of course, in problems where the fixed iteration does not converge. Yeah? Okay, let me stop it here.
Okay, so last lecture for today.